Francine used her warranty and replaced her phone. Now she's ready to go out on the boat again. This time she bought a new case. This case says that it will float and withstand 5 atmospheres of pressure. She thinks she should be safe. But before she goes on the boat, she wants to be sure. On land, Francine is going to determine whether her phone case will float or sink. How can Francine determine if her phone case will float or sink? Let's think about the forces that act on an object underwater. Suppose we have an object underwater. We've already determined that it has a certain amount of pressure at this point. We also know that since this point has a greater depth than the point at the top of the object, there's a greater pressure down here than up here. What that means is there's an overall upward push or upward force on any object underwater. We call that force the buoyant force. Archimedes' principle says a fluid exerts an upward buoyant force, Fb, on an object immersed in or floating on the fluid. Fb is defined by this equation. The buoyant force on an object is equal to the density of the fluid That's the density of the fluid the object is inside. The volume of the displaced fluid. There's a reason we say displaced fluid, because sometimes if an object is all the way underwater, it displaces the same volume as that object itself. But if the object is floating partway, like this object, it only displaces part of its volume. So this volume that's under the fluid is the volume that we're going to put into this equation, because that's the only part that applies a buoyant force. There's no buoyant force applied by the volume of the object that's outside of the water. So the volume is the volume of the displaced fluid, and then G is gravity, 9.8 meters per second squared. That's the buoyant force on any object. Now that we know what the buoyant force is, we can determine whether an object floats, sinks, or doesn't float or sink. To understand that, I'm going to define one more term, specific gravity. Specific gravity is the ratio of an object's density to the density of the fluid that it's in. We can also write this as Sg equals density of sample over density of fluid. We're using sample to represent the object, so density of sample is the density of the object. Let's consider 3 different cases. In the first case, we have an object and it's in fluid. It has 2 forces acting on it, the buoyant force from the water and the force of weight of the object. You can see that the force of weight is greater than the buoyant force. If the sum of forces is not equal to 0, in this case it's not, it's going to accelerate. And you can see that there's an overall net force in the downward direction. So this object will sink. The object sinks because its buoyant force is less than the force of the weight of the object. For this object, it's also true that the density of the sample is greater than the density of the fluid. This means that Sg is greater than 1. When Sg is greater than 1, the object sinks. In our second example, you can see that the object is in the water or in the fluid, and the buoyant force is greater than the force of the weight. In this case, there's an overall net force upward, so the object floats. This is true when the buoyant force is greater than the force of weight. It is also true in this case that the density of the sample or object is less than the density of the fluid, and Sg is less than 1. This is going to be what we want to happen when we have a boat. For a boat, the density of the submerged section has to be less than the density of the fluid that it's in or the water. So this is the reason that a boat is going to have air in the bottom of it, on the inside, to give it less density than the fluid that it is right next to. Our final example has an object, and this object has a buoyant force and a weight, a force of weight, that are equal to each other. This object does not float or sink. In this case, the buoyant force equals to the force of weight. The density of the sample equals the density of the fluid, and the specific gravity equals 1. So this object will just stay in place wherever it falls. Now that we have all this information, let's help Francine determine whether her phone case will float or sink. One way to solve this is by looking at the density of the object. So let's find the density of the phone case. If you remember, density is equal to mass of the phone case over the volume of the phone case. Now her phone case, we're going to have to include the mass of the phone inside it also. The mass of her phone is 0.115 kilograms. Her case is not much more than that. The mass of her case is 0.05 kilograms. Together, the mass for this calculation is going to be 0.165 kilograms. What about the volume? The volume will be the length times the width times the height. Fortunately, her phone case is a perfect rectangular prism. The dimensions of her phone case are 13 centimeters by 7 centimeters by 2 centimeters. Before we calculate the volume, let's convert these into meters. 0.13 meters, 0.07 meters. Multiply these together to get the volume of the phone case, and it is 1.82 times 10 to the negative 4th meters cubed. Then we can calculate the density of the phone case by doing the mass of the phone case over the volume of the phone case. The density of the phone case is 906 kilograms per meters cubed. If you remember, the density of seawater is 1030 kilograms per meter cubed. Her phone case with the phone in it has a density that is less than seawater, so the phone case will float.